This conference will now be recorded.
Okay, so good afternoon, everyone, and welcome back to a fresh new session on credit risk modeling using SAS. And in the last session, we were talking about the CCAR model development in the linear regression framework, right? So, so our object, so we were in a stage where we were kind of developing the, uh, we were kind of developing the first versions of the linear regression model, first version of the model to predict the time deposits, the percentage demand and the time deposits as a function of the rate of interest, right? The 3 months treasury rate. Now, having said that, if you have a look over here, so you'll see that. So what I have over here is the development data, right? So we have the. So what we did was we had divided the data into two parts. Number one, we had divided the data into. So the overall vintage of the data was from 2000 to second quarter to the fourth quarter of 2016. Now, from modeling vintage and out of, and we have divided them into modeling vintage and the out of time vintage. The modeling vintage being between 2000 to Q2 2014 Q4, and out of time vintage being between 2015 Q1 to 2016 04. Right? So we had divided it into these two parts. And so what we did over here was, so with the data from 2015 Q1, sorry, 2000 to Q2 to 2014 Q4, we had developed the model, right? And we were kind of exploring the different aspects of the model, right? So what we were kind of doing is we tried understanding, the different objectives of this model, the different outputs that this model has. So basically, what we did was we looked into linear regression. We ran the linear regression, and we started by assessing the parameter estimates. So one very important thing that we saw over here in the parameter estimates was that your treasury rate is something which is very important, right? Now, if you have your treasury rate, so your treasury rate is positively related to the demand of the time deposits, and what we also saw was that this was statistically significant, and if the treasury rate was reduced to zero, people would not be putting in any more funds or would not be demanding any more of these. They would not be demanding any more of these time deposits. On the other hand, what would also happen is, or what might also happen is, they may change, they may actually withdraw whatever they have, because they would have other assets where they could invest it for a proper with a proper return, and hence the intercept is negative. It says that the time deposits, or the percentage change in the demand for the time deposits, would be negative if the treasury rate was set to zero. So this is something that we had, and then what we have over here is the goodness of fit. How is the so then the next thing that happens over here is the analysis of variance. So then what we did was, once we assessed the model component, the next thing that we started looking in over here was that how is it that we can assess the overall fit of the model. So one of the goodness of fit test over there was the analysis of variance, and we discussed that how is it that this analysis of variance would help us assess the overall fit of the model. So one thing that we saw was that this analysis of variance table gave us an idea about how is it that the explained variation to the unexplained variation changes, right? So having said this, what we do over here is, so we saw that yes, the overall fit of the model was good, and the proportion of the explained variation was much higher compared to what we have, compared to what the unexplained variation was. Now, finally, the next part that we have is to use this root MSE and the R square. And so now what we need to do is we need to assess the overall goodness of fit from a second perspective, and that second perspective is the R square. So over here, what we are trying to do is we are trying to assess that that out of the total variation which was there in the model, how much has this particular variable been able to explain. So the question that comes out over here is the following. So the question over here is that, so how does this table, how does this root mean square error dependent mean, the R square adjusted R square, how would this table help us, right? So, so how does this table help us infer about the overall fit of the model? Right, so this is what the next question is. So the next question that comes out here is that how does this particular table, right, how would this help us in uh, assessing the overall fit of the model? So basically over here, so this table gives us an this table helps us analyze the proportion of the total variation which is explained by total variation in the dependent variable or time deposits in time deposits which is explained by the the treasury rates. So this table gives us an idea about the proportion of the overall proportion of the explained variation, the explained sum of squares relative to the total sum of squares. So what we get to see over here is that this table gives us an idea about the proportion of the explained sum of squares relative to the total sum of squares. That is up to what proportion, like up to like what proportion of the total variation in the dependent variable has been explained by the independent variable, and that is precisely what we have over here, right? So this table says that nearly 45% of the total variation in the change of time deposits is explained by the treasury rates, right? So so this gives us an idea that the variable treasury rate is a strong variable to assess the demand for time deposits, right? So over here, what we have done is, so what we could do over here is we could see from combining these two tables, the analysis of variance table and this R square estimate, right? What we could clearly see is that this particular variable is actually a strong variable, right? Which helps us in explaining the variations in the dependent variable, right? So this helps us analyze the proportion of this relative to this. So now from here, one thing that we have seen is that the individual regression coefficients are statistically significant and the overall fit of the model is also very strong. So therefore, this model appears to be a good model. Now the next question, the final question that comes out is, that is this an optimal model? Now this will be an optimal model if the residuals are white noise, because if the residuals are not white noise, it means that still there is something which can be explained but is not being explained, and that is why the error terms still have certain deterministic components in them. So that is the next part. So the final table that we need to look in over here is that of the IID, that is of the specification test.
I have one question in that R square.
Yeah,
Can you
tell
go
me.
to that once?
Just a second. I'll just paste this table and then I'll take the question. Just give me a
Yeah.
second. Yeah, tell me.
So, how is this coefficient of variation calculated here?
So
599.2
coefficient of variation is nothing but the standard deviation by the mean.
standard deviation?
So by the
Yeah.
mean. So basically you have the mean over here, right? If you calculate the standard deviation of the dependent variable, right? So hold on. So let's say this is yours, there's 0.00531, right? Okay. So let's say I have this standard deviation. So there's a standard deviation. This is the average. So now if I do this, standard deviation by mean, hold on. Hold on. Ah, so this coefficient of variation is nothing but this root mean square error, this divided by the mean into 100. So this is how this coefficient of variation is calculated over here.
Okay. And one more thing is, how could we say that,
Mhm.
45%, so you have 45% of the total variation is being explained. We're saying
Mhm.
that it is a, I mean, it's a good stat. So, I remember there's a limit, right? Like, how can we access that? Like below this, if R square is below some particular
No, no, no,
value.
no, 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 no. There is nothing like that. There is nothing like that. So you don't have any cutoffs on R squares. So what happens is, so this is to some extent this is judgmental, right? The reason it is judgmental is, let's say you have one single variable which explains 45% of the variation, right?
Mm-hmm.
So what it means is that whatever other variables, if you incorporate it into the model, they will together give you an additional 55% of the, will explain 55%. So if you add the variable, so the marginal contribution of the added variable will always be less than or equal to 45%, right? So if you add, let's say, three variables or two variables after this, and your model R square improves, and let's say your adjusted R square goes up to 80%. So it means that the remaining three variables together has added on to your model. So marginally they have added out like another 30-35%, the three variables together. So anyways, this single variable is explaining 45%. So that means this variable is one of the strongest variable to explain the time deposit, right? So given that it is one of the strongest contenders, and the second thing is it satisfies all the assumptions, or it is satisfying like all the results, satisfying all the required requirements of a linear regression output. So that is why I am saying that this particular model is a strong model. It is not because only it is 40 the it explains 45%, but think about it this way, that if this one single variable explains 45 more than 45%, it is actually more than 45%, right? It's like 46%. So the other variables can add on to 54%. So the marginal contribution made by any other variable to this model will be less than 45%, right? So it is this variable on its own which is impacting for explaining 45% of the dependent variable. So that makes this a very strong variable, right? So if you
Yeah, yeah.
add one more variable which can explain, which has the capability to explain 45% more variation, you will be explaining 90% with those two variables. So in all cases, in all probabilities, all the other variables, the marginal addition made by the variables, other variables, will not be as high as 45%. That is the reason why we are kind of saying that. So again, there is been a loss of degree of freedom, right? So if you adjust for that, the model is explaining 44%. So so whatever the thing is, but this variable alone is a strong contender in the sense that it is explaining a majority of the overall variation.
Okay.
That is why I am saying it's a good model.
So, yeah, okay. So, Tanmay, like here we have only one variable, right? And the R square is 45%. So,
Yeah.
with this one variable, this adjusted R square is 45%. So, what can we infer
What
from
if
this adjusted R square?
so why is this happening? Why is the adjusted R square falling? We had discussed this, right, Richard? So the adjusted R square is falling because as you are adding on a new variable, so when you had the intercept, only intercept model, so the only intercept model would have given you, so you would have a lot of degree of freedom, but with one
Only.
more variable being added, you are losing out a degree of freedom, right?
Yeah,
So
yeah.
you are gaining an increase in R square, you're gaining an increase in your, you know, in the overall explanatory capacity of the model, but you're losing out a degree of freedom. So you need to understand that whether this variable was worth increasing the, so worth the increase or not. So the increase in R square was worth the loss of degree of freedom or not. So that is where your adjusted R square comes in. So in your adjusted R square, what you are essentially telling us is that so when I incorporate this one variable, I lose out a degree of freedom, but even after adjusting for that, I have 44% of the overall variation explained. Now, if you were to do this with only the base model, you would see that this R square is much lower, and the AIC or the SBC of this model, or the archaic information criteria of this model, AIC of this model, would be relatively lower. in that only intercept case. So as you move from the only intercept to one variable case, you see an increase in both, and that is where you know that this model is giving you a good fit. So after adjusting for the loss of degree of freedom, because I incorporated a new independent variable, the after adjusting for that, my degree of percentage is like 44%. So that
Yeah,
is precisely what adjusted R-square is.
yeah, yeah.
Right? Okay. Okay. So the final table that I have over here now is the specification test table, which will give me an idea about whether the term is a white noise, whether the error term is a white noise error term or not. Okay, so this is the test of white noise for residuals. Okay, so if you have a look into this part, now this is the specification test, right? So the question over here is that how do we test for white noise? Test for white noise. Okay, so this is the specification test. The specification test. Okay, so specification test. So first of all, what we'll talk about is the test hypothesis. So when I talk about the test hypothesis, so the test hypothesis over here is, this is So the residuals are identically and independently distributed, so that they are IIDs. Versus HA, the residuals are not identically and independently distributed. So this is the first test hypothesis, right? Now over here, the objective is, now if my null hypothesis is accepted, what it essentially means is that the error terms are identically independently distributed. That is, they are white noise, right? Or that they are, so there is no autocorrelation or heteroscedasticity in the distribution. So that is where the residual, so that is where the test hypothesis works, or that is where you identify this test hypothesis, right? Now the next question that comes out over here is, so how is this decision taken? Now this is again taken by comparing the p-values with the level of significance, and the level of significance, as we have clearly said, is by default held at 5%, right? So over here what we have is the p-value, which is equal to 0.2572, is the actual probability of committing the type 1 error. So the actual probability of committing the type 1 error. The level of significance, or the maximum affordable level of committing the type 1 error is 0.05. So the actual probability, the actual chances of committing the error, are much more than the accepted levels. Therefore, we do not take the risk of rejecting the null hypothesis, Instead, we accept it. Given we have accepted the null hypothesis, we can clearly say that the error terms are not characterized by autocorrelation and heteroscedasticity. Okay, so this is something that we have over here. So therefore, we do not take the risk of rejecting the null hypothesis. Instead, we accept it, and hence what we can say that, so given that we have accepted the null hypothesis, we can say that the error terms are not characterized by autocorrelation and or heteroscedasticity, and hence the error terms are white noise. Now, given that the error terms are white noise, all our required specifications are satisfied. Now, we know that number one, there is this particular you know there is this particular part, right? So this particular model which is there, and what you can see from here is you can see that the variables are statistically significant, the regression coefficient is significant, the analysis of variance results are good, the r square is pretty good, and also what you get to see is that the error terms are white noise. So this first version of the model is ready with us, right? Now what we need to do is the final check that we need to do over here is we need to assess the accuracy of the model, and from there also we need to assess the residual plots. So we need to do that, and we need to kind of benchmark the results of accuracy and the residual white noise test from this particular function. So that is something that we need to do. So okay, guys, just give me a minute, huh? I'll just be back. Just give me. Hello. Guys, I just have a urgent call to take. Okay, it might just take me around 5-10 minutes. I'll just be Okay, just hold on. I'll just be back in the next 5-10 minutes. I just have something urgent to attend.
This conference will now be recorded.
Okay, so sorry. So as I was saying, right, that the model now is more or less finalized. So I can see that the single variable model is all good. Now the next thing that I need to address for is I need to understand the accuracy of the model. So how accurate has this or is this model like? So how is the actual versus predicted accuracy of the model? So first what we'll do is we will do a back testing on the data for which we have both the observed and the predicted values, right? And then we will implement this model in the next periods, right? We'll validate in the out of time as well. And then from the point of time when we don't have the values, that's called the jump off point, we will be using this model. So we will be next, so our next task would be to validate this model on both the model development and on the validation data, right? So let's have a quick look over here. So this is the raw data that we have. So now we had divided this data into development modeling vintages and out of time vintages. So over here, what we'll have is the model iteration one. So model iteration 01. So first, we'll have this table 02, table 02, the time series data development. So this is something which is work prediction. Now these values that I have over here, these are your observed values, right? Now this is the independent value variable. Now over here what we'll do is I'll have the predicted values, FPRTD predicted. Okay, so how do I get this predicted series over here? So my predicted series over here will be this plus this star this. Okay, so this is the model intercept. Intercept, and this is the slope. Okay. Have this plus this into this. So I need to fix these cells. Okay, so now let's have a look into this prediction, into the accuracy of the prediction, right? And whatever is not predicted will be your residuals, right? So the actual minus the observed will be your residuals. Okay. So this is the actual minus the predicted. Okay. So now what we'll do is we'll kind of plot the actual versus predicted and the residuals first, right? So these are the two plots that we first need to do. Okay. So now if you have a look into this model, right? So from here, what I can clearly make out is that there is a serious accuracy issue in this model because Like, yes, when the rates of interests are going down and everything is fine, but the challenge that you get to see over here is that the volatility that this particular series has is not actually, or is not really captured through this particular model. So even though I have kind of implemented this model and I see that everything looks fine, but the challenge that still remains over here is that no, this series cannot capture that extent of that volatility which is there in the model, right? Because so one specific reason here, because I mean, one specific reason here is because maybe one of the main reason is that this is a no lag model and it's the most simplest of the models, right? And the non-linear behavior has not really been captured in the series. Now also the PRTD, or the time deposit, is a very volatile series, right? So one thing that we need to address over here is, so we would be trying out other versions of the model as well. But one important thing that we need to take note of in this part of the story is that okay, so this is actual versus predicted plot. Actual versus predicted plots for PRT. So, so one thing that I gradually get to see over here is, right. So, if you have a look into this, you'll see that there are some periods when this is actually kind of very nicely it's predicting, right. So it's predicting at a point of time, right. So if you have a, yeah, so if you have a look into this, you will see that there is a part in this particular phase where it is correctly more or less predicting, but the volatility which is observed over here in this part is something which is not identified, because the moment your rate of interest goes to zero, this falls flat, right? So one problem over here is that this is a very non-linear movement in this graph, which we are trying to capture using the linear models, and hence there is a gap, right? So there is a gap in this first version of the model, as we had already, kind of uh, like discussed right in the beginning, that whenever you have developed this particular model, so then the next part that you need to look into is you need to try out other versions of the model. Treasury rates, right? So one thing that we get to, one thing that we see very, what I would kind of tell you is that, so this is something that we really look into in this particular model, that when we are using this linear regression model in this particular series, without any lags or without any kind of transformations, or without performing any sessionality checks or anything. So when we're just building the first model just to understand how this model would work, even though the model is performing fine in every aspect, we see that the model's capability to actually capture the fluctuations, right, in terms of volatility is actually very different. I mean, so it's not really very, so this model does not really prove useful after the rates of interest goes down to zero. So in this particular phase, where whenever there may be multiple instances where the rate of interest has been around zero or close to zero, in such a regime, this particular behavior or this particular model really turned out to be very different, right? So its performance has not really been able to capture any of these movements. So there has been periods of over prediction, there's been under prediction, and mostly under prediction in these cases, right? So it has always remained below what the actual path has been. So in this particular zone, it has been kind of a failure, but in this other parts, right? If you plot to these other parts, right, you'll see that yes, there is a good behavior. So this volatility, which is towards the end of the term, right? But the rate of interest really fall flat. So this movement in the time deposit bond really shows that it is kind of independent of the treasury movement. So it is not only, so there are some other factors so which we can also identify from here, that to this treasury bond there can be other factors which is perhaps driving this particular model, right? So there could be other related interest rate factors, or there could be other speculative factors, or there could be a whole set of other factors which is impacting this particular movement. So in this particular zone, so if I use my model over here, right? So if I use my model in this zone after it reaches zero, that is, if you have a point, look into this particular point, right? So let's say, say in a zero interest rate regime, right, where the rate of interest is literally zero or it is very close to zero, in such a case this model will not be able to capture the movement in the time deposit. So there must be some other factor, let's say a substitute factor or an alternate, which will cause the demand, or whose a movement in which will cause a movement in the demand of this particular, the demand of this particular asset. So looking into this, looking at it from this perspective, we can say that yes, there is no. Like looking into this perspective, looking from this perspective, we can say that yes, in this particular region where you have like very low rates of interest, just nearing zero, in such a case, this model is not really a good fit, and this kind of making certain extent over predictions with sensitiveness to the rate of interest. So there could be an alternate variable. There should be an alternate variable which will help me control the movement of the time deposits when the rate of interest is zero. So if the treasury bond demand is zero, then the demand is not always zero. So there is some element, some other element which is causing this. So the amount of, the extent of variables that I have with me in developing this linear regression model is not a sufficient model. So there must be other variables which should guide me to, to have to take the model the way we would want, because in this part, in the 2014, the late 2009, right, 2008, 9, so from where the rate of interest started really going down, right? So in that phase, what we see is that there is a fluctuation in the treasury bond, but the rate of interest are falling flat. So there is something else apart from this rate of interest which is causing those fluctuations. So there is a variable which is missing out there, and that is the variable that we need to identify, right? And that will precisely be the second version of the model. Now, another way it could be is that this movement is because of lags, right? Let's say, so over here, this is the zero lag model that I have tried out, right? I got certain results, but yes, in terms of accuracy, the accuracy was much lower. because one thing that I can clearly see is that it has fallen out from this part, right? So it has actually fallen down. So the accuracy is actually fallen down because in this volatile portion, even though the trend is more or less being shown, but it is unable to kind of capture that part. So we will have a look into this accuracy as well. And over here we have months. The months. Now the next part that we'll do is we'll plot the residuals. So now have a look into this residual. So this is basically your residual plot. Now, can you find any pattern in this residual plot? So because this residual plot does not have an increasing pattern or it does not have a decreasing pattern, so it does not have any pattern whatsoever involved into this. So that is the reason why this particular part or this particular version, has so over here I can say that the residuals do not have any pattern into them, and hence this residual is a white noise residual. Also, when you have a look into model iteration, into this first version of the model iteration, right? We have model intercept, we have slope and everything. So over here again, so the next part for us would be to compute the accuracy. So the accuracy will be computed as 0.02. So basically, I'll have the residuals, right? The actual minus predicted. I'll square them up. I'll add and I'll divide by n. So what I get is the mean square error, right? So mean square percentage error. So I'll compute it as a percentage of the actual value. I'll square that, and from there, what we'll do is we will kind of generate the accuracy, right? So let's get started on that. Residual plot, saturation 0, 1. So over here, what I have is the months. Okay. Okay, so these are the three results, or these are the three major graphs that we'll have from the first iteration. And from the first iteration, there is one thing which is very common, and which I can clearly see from this exercise is that the accuracy of the model appears to be pretty weak, especially in that point where the model, there is a volatility after 2008, but that is not totally captured through the rate of interest, because the rate of interest have again gone down to nearly zero. Right. Okay. So the next part is the error calculation. So this is the mean percentage square error. So over here, what I'll do is percentage square error. So percentage error, right? So the residual divided by the observed. Okay. So what I have is the mean square percentage. So I have the square percentage error over here. The next measure of accuracy is the mean square percentage error. Okay, so over here what we have is mean square percent error. Okay, okay, so mean square percent error. So this is Okay, so the mean square percentage error over here is your 17.48. So, but which is again, which is quite a bit, because you should, so your accuracy has to be very close to the actual value. So over here you have your mean square percentage error as 17.48, then that's pretty then that's pretty that much of a concern. And also, even though if it was not much of a concern, then what we would do is we would ideally require us. So what we would ideally do is we would kind of give him, or so basically cover the future percentage error. So we would kind of now try to develop other alternate models, right? And once we develop these other alternate models, we'll compare their MSPs, we'll compare their AIC, then we check which is the model with the least MSP, and then that model will be passed through your adverse, severely adverse, and your baseline scenarios, and your marker and your estimates would be obtained to see that which of them is giving us a better estimate, which of them is giving us a better, which is giving us a better uh, and a more robust estimate. So that is what we need to do next. So I have completed the application of linear regression model in Excel, like on SAS for this CCAR thing. Right now, it's obvious we'll try out these other models. We'll try out a lag model over here, and we'll try out a log. No, log model will not be possible because there are negative values. So we'll try out a lag model, and if that lag model doesn't work, so we compare that lag model and this model. Then we'll introduce another variable to this to take care of these fluctuations happening from 2008 Q4 onwards to 2016-04. So that is something that we need to take care of, right? So this is something that we'll continue doing with it. So for the time being, first go through this Excel sheet that we have prepared, walk through this, look through the comments, the content, the code sheets, the output and everything, and get an idea of how linear regression needs to be implemented. And then what we'll do is we'll work on the other alternate models, right? Okay, and so I'm sharing over this document and the this file with you guys, right? So I'll share them over so that you can start working on them. I've completed the first version of the model. The next version of the model we'll talk about is a lagged model, and then we'll again do a linear regression. We'll see how it works out. And if that doesn't work out, then we'll start treating the variables a little bit. We'll try looking at the distribution. We'll try still again looking into whether it's stationary or not, how is it behaving, and so on. And then we'll redraft the third version of the model. So these would be the three respective versions. The first is without any lag, without repeatment, just simple linear regression exercise. This will form your base model. So that whenever you do any enhancements, so that must be reflected as a lower MSP in your model. So the model that you build next must have a lower mean squares of errors, right? And then the model that you build will again have another lower part. So it must operate that way, right? Okay, so thanks a lot for your time, guys. Let me share this off, and then you can go through it over the week, and we'll catch up next week. Thank you. Bye bye. Have a great week ahead.